In this video, we're going to do a variety of basic vector computations. We're going to add vectors together, we're going to subtract vectors from each other, we're going to multiply vectors by scalars, things like that. Basically just boils down to doing some basic arithmetic on the different dimensions of a vector. So as a first example, we're going to work with the vectors x and y. These are two-dimensional vectors. Each vector x and y has just two components, and we're going to do a variety of computations. So in part A, we're going to compute x plus y. So since x is defined as the vector 1, 2, and y is defined as the vector negative 4, 6, that means we need to take the vector 1, 2 and the vector negative 4, 6 and add them together. And the way that we do this is we just do it what we call component-wise. So this first element of x and the first element of y, we will add those together. So 1 plus a negative 4 is a negative 3. And then similarly, the second component of x and the second component of y, we will add those components together. So we end up with the vector, single vector, 1 minus 4 and 2 plus 6. So this is what we mean by doing kind of component-wise addition. And then at this point, this is almost trivial. 1 minus 4 is a negative 3, and 2 plus 6 is 8. We'll do a similar thing when we do vector subtraction. For vector subtraction, x minus y, we're going to take the vector x and we're going to subtract the vector y. And again, we do component-wise operations. So we'll subtract the first dimensions of the vectors. We'll subtract the second dimension of the vectors. So this turns into 1 minus a negative 4 and 2 minus 6, which again is very simple. That's just 5 and a negative 4. And then as a final example, let's compute the quantity 3x plus 2y. So we're going to take the scalar 3 times the vector x, and then we're going to add that to 2 times the vector y. So if we write that out, that's 3 times the vector x plus 2 times the vector y. When we have a scalar that multiplies a vector, which is what we have right here, we have the scalar 3 times the vector x, we just take the scalar and multiply it by every single component of x. So we're going to write down 3 times 1 and 3 times a negative 2. So that is 3 and 6. And then similarly, this scalar times the vector y, we're going to multiply every component of the vector y by 2. So a negative 4 times 2 is 8, or negative 8, I'm sorry, and 6 times 2 is 12. And then we just have vector addition. So we're back to doing things that we started off this example with. We just add these component-wise. 3 plus a negative 8 is a negative 5, and 6 plus 12 is 18. So that's an example of doing some very basic vector operations: addition, subtraction, and then basically a linear combination of vectors. So this linear combination is kind of a superposition of a linear combination of vectors. And we did that for vectors that have length 2. Let's go ahead and do it for vectors that have length 3. So now we're going to let x be a vector that is equal to negative 1, 2, and 4. I'm sorry, the vector a is equal to negative 1, 2, and 4. And b will be equal to 0, 2, and 7. And we'll do the same type of computations again, but now we're dealing with vectors that are just a little bit longer. So if I want to compute a plus b, conceptually it's the exact same thing. I write down a, I write down b, and when I do vector addition, I add each piece of each vector component-wise. So a negative 1 plus 0 is a negative 1, 2 plus 2 is 4, and 4 plus 7 is 11. So that's almost trivial again. If we do vector subtraction, let's go ahead and do b minus a this time. So I write down vector b, I subtract off vector a, and then again we do this component-wise. So I'm going to write down 0 minus a negative 1, 2 minus 2, and 7 minus 4 in vector form. And then evaluating this quantity is very simple. 0 minus a negative 1 is 1, 2 minus 2 is 0, and 7 minus 4 is 3. And then let's go ahead and do a linear combination. So let's compute the quantity a negative b plus 3 times a. So a negative, the vector b, is like I'm multiplying vector b by a negative 1. So that turns all the elements of b to their negative quantities. So 0 times a negative 1 is 0, 2 times a negative 1 is a negative 2, 7 times a negative 1 is a negative 7. And then I'm going to add that to 3 times a, so we just distribute the scalar multiplication. That turns into a negative 3. 3 times 2 is 6, and 3 times 4 is 12. And now we just have basic vector addition to perform. We do that element-wise, so I end up with 0 plus a negative 3, negative 2 plus 6, and a negative 7 plus 12. So if I add all those up, I get a negative 3, 4, and 5. Obviously, we could keep going. We could do another example with 4-dimensional vectors or 5-dimensional vectors or n-dimensional vectors. But conceptually, these are all going to be the same. When I add vectors, I add their components. When I subtract vectors, I subtract their components. And when I multiply a vector by a scalar, each component of the vector gets multiplied by the scalar quantity.